Hello, welcome to today's tutorial. Today we're going to do question 9, 10 and 11. So these questions were also given in the assignment, but then I thought because there are some people who had said that they had challenges solving the questions, so I thought of going through so that you see the mistakes you are making. We're not going to have a Zoom meeting for this. We're just going to have to look at this and correct the mistakes that you had been making as you were doing the assignment. Okay, so question 9 reads, a cooler box used to keep drinks cold has a total wall area including the lid of 0.8 square meters and wall thickness of 1 centimeters. It is filled with ice and cans of orange soda at 0 degrees Celsius. What is the rate of heat flow into the box if the outside temperature is 30 degrees Celsius? So from this, the information that I've just read, I can collect the data. The data that's there is we've been given that the thickness is equal to 1 centimeter, which is equal to 1 times 10 to the power negative 2 meter. Then we have been given the area of the cooler box together with the lid, which is 0.8 meter squared. We've also been given the temperature at which we are starting, which is 0 degrees Celsius, and the final temperature, which is T2, and that is 30 degrees Celsius. The other information that we've been given is K, which is equals to we've not been given K, but we've been given actually. The question has K of the cooler box, which is equals to 0.01 joules per second meter degrees Celsius. Okay, that's the information we've been given. Then we've also been given the heat of fusion, which is equal to 335,000 joules per kg. So this is the information that we've been given in this question. Okay, so now how do we go about solving the first part of the question, which reads, what is the rate of heat flow into the box if the outside temperature is 30 degrees Celsius? Okay, so because the outside temperature is 30 degrees and the internal temperature is 30 degrees, so just with here we'll have the change in temperature, which is equals to 30 degrees Celsius, because we are going to have T2 minus T1, which is 30 minus 0, which takes us back to 30. All right, now we know that the rate of heat transfer is heat divided by T, or dQ divided by dt. Okay, this is also equal to the constant K multiplied by the area multiplied by the change in temperature, everything divided by change in air, okay, which is in this case the thickness. All right, so from the information that we have here, we've got K, we have the area, we have the change in temperature here, and we also have the thickness, which is the L. So we can substitute and we'll be able to get what we actually want. Okay, so I'm just going to go ahead and substitute the 0.014K times 0.8 for area multiplied by the change in temperature, which is 30 degrees, and divided by the thickness. In this case, the thickness is 1 times 10 to the power negative 2. So that's what we have. And if we simplify this, we are going to get our solution being equal to 24 joules per second. Okay, so that's the rate of heat flow into the cooler box. Okay, if the temperature outside is 30 degrees, the heat flow is going to be at 24 joules per second. Then we go to the second part of the question. So this is the first part. Then we go to the second part. The second part says how much ice melts in one day? Okay, how much ice melts in one day? We all know that one day has got 24 hours, isn't it? So we have got 24 hours multiplied by 3,600 seconds. 3,600 seconds make 1 hour, so multiplied by 24, that will give us for the whole day. So this will give you 86,400 seconds. So these are the seconds that we have in a day. Okay, now the question that we just solved on top told us that the heat is transferred at 24 joules per second. So if that is the amount of heat that is being transferred per second, and we have 86,400 seconds, so then how much are we going to have? So we're going to use the formula MHF. Okay, MHF being equal to the mass of the ice multiplied by the heat of fusion, and that should be able to give us the amount of heat that can be transferred in a day. So in just 1 second, we have got 24 joules per second. Then joules, okay, we have got MHF, which is going to give us 24 joules per second, multiplied by how many seconds do we have? 86,400 seconds. So that will be seconds per day. Okay, so that will end with the day, then the seconds will divide out. Okay, now we don't know the mass. That's the one we are actually looking for, the mass of the ice. Okay, so now we are going to substitute. We don't know m, we're going to make m the subject of the formula is equal to. So if I multiply 24 by 86,400, I'm going to get 73,600 joules per day, divided by the heat of fusion, which is 3, we've been given 335,000 joules per kgs. Okay, so that's what we have. If we simplify this, we are going to get, we'll end up with the mass being equal to 6.19 joules. Oh, sorry, 6.1, because the joules will divide out, we'll have 6.19 kgs per day. So this is the amount of ice cubes that we are that's going to melt in a day. In that, you can obviously write it as 6.2 kgs per day. So this is how the question was supposed to be solved. Okay, in a case that you made mistakes, this is the correct way to go about it. So that's about question 9. Next, we'll go to question 10. So question 10 reads, a solar collector has, sorry, I'm not going to be showing you where I'm reading from. I'm reading from actually a soft copy that's just on a desktop. So a solar collector for a hot water system absorbs solar radiation at the rate of 660 watts per meter squared. Its collecting area is 3.8 meters squared. Cold water at 15 degrees Celsius enters the collector. What volume of water per minute at an output temperature of 60 degrees Celsius can this collector deliver? Okay, so in this situation, we can collect the information that we've been given as usual. We have 660 watts per minute squared as the heat per unit area, and then we've been given the area to be equal to 3.8 meter square, and then we know the temperature we are starting with is 15 degrees Celsius. We want to get to 60 degrees Celsius. That's the temperature we want to get to, right? So the question asks us what volume of water per minute at an output temperature of 60 degrees can this collector deliver? Okay, so we've been told that this collector has it absorbs solar radiation at the rate of 660 watts per meter squared. Okay, so for every meter squared, it is able to receive 660 watts. So now we've been given 3.8 meters squared. So we need to find out how the total amount of heat that we are going to be expecting with this collector. Okay, so we are going to say 660 watts per meter squared multiplied by 3.8 meters squared. If we multiply this, we are going to get 2508 watts. Okay, so this is the total amount of watts or energy that we are going to absorb with this collector, the total energy. Okay, so now the question asks us how much, and this is in watts, meaning this will be equal to joules per second, isn't it? Okay, so now we want to find out how much of the energy we are going to need. So, of the mass. How much of the mass are we going to be able to convert or to change the temperature from 15 degrees to 60 degrees with this amount of energy? Okay, so if we use the formula MC dt is equal to dq. Okay, then dq is the energy that we have calculated here, and if we want m, which is the amount, we are going to say dq divided by c dt, where c is the specific latent heat and dt is the change in temperature. Okay, so we already have the value for dq. It's just a matter of substituting. We'll have 2508 divided by the specific latent heat is 4184 multiplied by the change in temperature, which is equal to 45 degrees, right? The change in temperature is from 15 degrees Celsius to 60 degrees Celsius, so meaning the change will be T2 minus T1, which will be 60 minus 15, and that will give us 45 degrees Celsius. So that's what we are dealing with here. If we simplify this, we're going to get that the mass will be equal to 0.013 kgs. Now we'll convert it to grams, so that this will be equal to 13.3 grams. Now this is in kgs per second, right? Then this will be in grams per second. That's what we have. Now what if we were to convert it to grams per minute? How much are we going to have? Okay, so if we're converting it to grams per minute, then we're going to say 13.3 grams per second multiplied by 60 seconds divided by 1 minute. Okay, so the seconds will divide out and we'll have the minute remaining, and this will give us 799 grams per minute. Okay, so now this is in grams. The question asks us to find what volume of water per minute at an output of temperature of 60 degrees can this collector deliver? So this is in grams per minute. We need it to be in cubic centimeters, cubic meters, but the thing is it has to be in volume and not in mass. So the conversion that's there is that in terms of grams or mass to volume, 1 gram is equal to 1 cubic centimeter, right? So meaning 799 grams will be equals to 799 cubic centimeters, meaning that even our final answer will be equal to 799 cubic centimeters per minute. This is what we're going to end up with eventually. Okay, so grams to cubic centimeters. This is how question 11 is to be tackled. This is how you can solve it. Okay, now we can go to question 11. Question 11 reads, a hot tungsten wire filament has a radius of 0.060 centimeters, a temperature of 3000 Kelvin, and an emissivity of 0.74. Calculate the rate of energy emission by a 1 meter length of the wire. Ignore the radiation received from the surrounding environment. Okay, so with this question, from the question I've just read, the information that we've been given is that we have the radius of the wire, which is equal to 0.060 centimeters, which is equal to 6.0 times 10 to the power minus 4 meters. We've been told the temperature is equal to 3000 Kelvin. Emissivity E is equal to 0.74, and the thickness of this, or the length of the wire, is equal to 1 meter. Okay. So now, we've not been given the area of the wire, so I'll just put it there and calculate it. Since we use the total surface area when we are dealing with radiations and how much heat has been absorbed, we use the total surface area. So the total surface area for a wire will be equal to 2 pi RL. Okay, so R we have, L we have, it's a matter of substitution, and this will be equal to 2 pi multiplied by the radius, which is equal to 6.0 times 10 to the power minus 4, multiplied by 1, which will give us 0.0038 meter squared. This is what we're going to have as the area of this wire. Okay. Then now we can go ahead and do our calculations. So the change in heat divided by the change in time is equal to Boltzmann's constant, emissivity, the area multiplied by the temperature to the power 4. Okay, so this is straightforward. As usual, we just substitute. We have Boltzmann's constant is 5.67 times 10 to the power negative 8 multiplied by emissivity, which is 0.74, multiplied by the area, which is 0.0038, multiplied by the temperature, which is 3000 to the power 4. Okay, so this is to the power 4. Once we can now go ahead and calculate, this will give us 1281 2.4 watts. This is the energy that I had calculated, which of course you can get 12.81 to watts if you round it off to the nearest whole number. So this is what you are expected to do in your assignment. So okay, so well, that's all for this video. I'll prepare some more concerning the other questions as time allows. In the meantime, that's all for now.